name is Yutel from the imaging group of Muller Space Science Laboratory, University College London. And talk today, I'm going to give is about the imaging and 3D mapping of the Martian surface. And in particular, it's about generating super fine scale topography from Mars using the optical images, using single image 3D estimation and super resolution restoration techniques. Right. I will first start with some background about Mars optical imaging. And optical images are one of the most important and intuitive resources for studying a planet like Mars. And here's a figure on the left. In this slide shows a collection of some of the past and ongoing Mars orbiters carrying different remote sensing instruments. And the figure on the right shows a picture when Mars was first imaged in 1965 by the Mariner 4 spacecraft. And over the past 56 years, the same location on the planet has been observed by 6 other visible cameras with different resolutions. A lower resolution Mars optical images generally have a larger spatial coverage, but lower resolution of the surface, and they can be used for global scale exploration. But the high resolution Mars optical images generally have a smaller coverage of the surface, but they can be used for detailed investigation of specific local regions. So for example, this figure here shows where the ExoMars Rosalind Franklin rover was planned to land at Oxide Planium. And here's a 12.5 meter resolution HRC image mosaic. It's HRC image mosaic that covers the whole of Oxide Planium area. And this allows us to visualize the geological context over the whole landing site. However, when we zoom into a local area, we won't be able to see too much detail due to its limited image resolution. So for example, this crater here, having a width of about 800 meters, it's quite blurry in this HRC view. But if we switch to the 6 meter resolution Mars Reconnaissance Orbiter CTX image over the same area, and we can see much more finer scale details, like a sharper crater outline, sediments, bedrocks, and some linear features inside, which you cannot easily see in HRC. The next, if we switch to the 4 meter resolution ExoMars Tree Skies Orbiter CaSSIS color and photogrammetric images over this zoom-in area, we can resolve even finer scale detail, like this transverse ionic ridges inside this big crater here. So, however, if we continue zooming in from this bigger crater with several hundreds of meters of diameter to smaller craters with tens or a few meters of diameter, like this to just to the top left of the main crater, the details are generally missing. And finally, for a tiny 3% or 4% of the Martian surface, we can switch to the 25 centimeter resolution HiRISE images, which allows you to see details of many surface features, such as the fine scale features on the ridges of these very small craters. So my talk today consists of 2 pieces of work. The first of which is retrieving high quality 3D information from input of orbital optical images. And for example, for this zoom-in view of this HiRISE image, photogrammetric 3D information can be derived by matching 2 stereo HiRISE images. And this is an example of the 3D model produced by the University of Arizona using a commercial 3D reconstruction software called CaSSIS. And this is also the HiRISE official PDS planetary data system DTMs available. The color from this blue to red represents the calculated 3D height from the lower elevation to higher elevation. of each of the corresponding 2D pixels of the image on the left. So you may observe that the quality of the 3D model of this zoom-in area is not perfect, mainly due to the differences of image conditions of the left and right of the input images, and which may result in matching artifacts using photogrammetry. But what we can produce using deep learning techniques is like this, generally have much higher quality and accuracy. So we can observe that this 3D model has much fewer artifacts and errors, but contains a lot more finer scale details. And if we measure a 3D profile over this quarter ridge, shown as A to A prime in the left figure, we can get 3D information of all the small peaks on this profile line using the deep learning based 3D result we have generated. This is essential to geologists to study fine scale Martian surface features. And 3D model products like this one shown here was produced using a deep learning method that we have developed last year called MADNet. And MADNet is short for multi-scale reconstruction with generative adversarial unit for single input image 3D modeling. We also optimize the algorithm to MADNet 2, MADNet 2.0, and publish 2 papers that describe the MADNet systems, and the QR code that links to the papers are shown on the bottom left of this slide. So if you are interested, then you can take a screenshot to read the technical details. And the network architecture of MADNet 2.0 is based on the relativistic generative adversarial network, which contains a generative network to produce predictions of relative heights from the image, and a discriminator network to distinguish the predicted heights from the ground truth height and the training data set. The generator network uses a UNet structure, which uses the 4 stacks of dense convolutional blocks and as the encoder arm, and the 5 stacks of up projection blocks in the decoder arm. And we train the network using selected HiRISE PDS DTM, and our in-house processed CTX DTMs, which are both downsample to their effective DTM resolutions in order to perform pixel scale image to height training. So for example, we measure the effective resolution of the 1 meter per pixel HiRISE PDS DTMs to be actually lower than 4 meter per pixel. So therefore, we downsample the training HiRISE image PDS DTM, both images and DTMs, PDS DTM, both into 4 meter per pixel for training. And similarly, we downsample the CTX DTMs to 36 meter per pixel, the 6TX DTM also from photogrammetric pipeline. And in this way, the noise and the artifact from the photogrammetric training DTMs are mostly removed, and we can train the network to learn per pixel image to height predictions. After the network training, we then tested and published results to show that the trained model works for different Mars images regardless of their image resolution. And this includes HRC image, CTX, CaSSIS, and HiRISE images, because due to the fact that the most of the features on the Martian surface scaling can be considered as a scale invariant. And regarding the overall processing chain, we need to spatially tile an image to fit the size of the input of the pre-trained model. And we need to do multi-scale reconstruction in order to predict both the large-scale and fine-scale topography. And also we need to use a reference low resolution DTM like Muller to rescale the predicted relative heights into absolute height values. And these 2 figures show the flow diagrams of the 2 MADNet systems for brevity. MADNet 1.0 uses multi-scale inference plus single-scale reconstruction, but MADNet 2.0 uses optimized single-scale inference plus multi-scale reconstruction. So now we come back to this HiRISE image that was used to derive the previous 3D model. The second piece of this work is about super resolution restoration. And super resolution restoration refers to the process of enhancing the spatial resolution quality and resolvable details of a given low resolution image by combining non-redundant information, either combining non-redundant information contain multiple repeat observations or through predictions of the best high resolution solution using deep learning models. And given the physical constraints of the imaging instruments, we always need to trade off spatial resolution against the launch mass, useful source size, and telecommunications bandwidth for transmitting data back to the Earth. So currently, the highest resolution optical imaging system of Mars is a 25 centimeter HiRISE imager. However, the resolution of 25 centimeters is still not high enough to view super fine scale ground features such as individual rocks or sedimentary features that the Mars robotic rovers or a helicopter could do, even though for a very limited tiny area of the Martian surface. So if we continue zoom in from the 25 centimeter HiRISE image, will gradually reach the limits for its resolvable details. We then experimented with deep learning techniques for super resolution restoration, which allows us to start from a single input Mars optical image and to continue zooming in from here to see much more details of this tiny region, and or also to see more details of any other areas beyond this landing site area. So now let's zoom in a bit more and change the display contrast for this area only. And this is what we can see from our super resolution restoration result comparing to what we can see from the original 25 centimeter resolution HiRISE image. The super resolution images like this one shown here was produced using the MARSGAN system, short for multi-scale adaptive weighted residue super resolution generated after the serial network, and published a paper that describes the MARSGAN network and processing chain. And the QR code is given here if you're interested in reading the more details. And the network architecture of MARSGAN is also based on the relativistic generative adversarial network and containing an adaptively weighted dense residue network and a multi-scale reconstruction block for the generated network and a similar discrimination network of the MADNet model. So the network has been trained using a section of high quality HiRISE images and its low resolution counterparts containing a variety of unique Martian surface features. MARSGAN has been tested on many different sites and also on different Mars orbital images. For example, this slide shows the fine scale recurring slope linear RSL features as the Garni crater, which are linear dark stripes found from steep slopes of Mars and disappears and reappears in different seasons. And they are shown on the 25 centimeter HiRISE image on the left and the super resolution result on the right. And here's another example of a crater feature at Oxapolonio on the 4-meter resolution CaSSIS image on the left and the super resolution result on the right. Now let's zoom in more to these bounding boxes. We can see the details resolved using MARSGAN on the right and comparing with the original 4-meter CaSSIS image on the left. And now what's more interesting is that we can combine the super resolution processing with the 3D prediction network I've just introduced to produce super resolved 3D models that have even higher resolution than the input optical image. I call this Super-3D here. And as an example of this, a figure on the top left shows an example of the original 4-meter CaSSIS image is super resolved image on the top right, and the best possible 3D model at 8-meter resolution derived from the original CaSSIS image using MADNet on the bottom left, and the 2-meter super resolved 3D model on the bottom right, which is the subpixel scale to the original input CaSSIS image. You can scan the first QR code to read the paper that was published early this year. Early this year, and to download it and take a look of the 3D model as well. Shown some broad figures here using the second QR code. And here's another example. This is over the ExoMars learning set, oxide planning. If we zoom into this to this green bounding box here, we can see the 25-centimeter HiRISE image, and continue zoom into the orange bounding box and remove the overview map, and let's see visually the comparisons of the super resolution and 3D results of this area. And here on the left are the super resolution and the super 3D results of the CaSSIS images in comparison with the reference 1-meter HiRISE PDS 3D model and the 50-centimeter HiRISE MADNet 3D model. We can see that using MARSGAN super resolution and MADNet 3D estimation, the details of the super 3D model, which is this row here. This is a super 3D model from CaSSIS, and this is in comparison with the HiRISE PDS DTM and HiRISE MADNet DTM. So the details of this super 3D model are almost at the same level of the best possible 3D models that produced from the much higher 25-centimeter HiRISE images. And now let's zoom in further for smaller area inside this blue bounding box, and here's what the 25-centimeter HiRISE image looks like. And on the left are the hill shaded super 3D result in comparison with the other hill shaded 3D products, as well as the original and the super resolved HiRISE images. We can see how much 3D details we can retrieve here on the last row using a combination of the MARSGAN super resolution and the MADNet 3D estimation out of this 25-centimeter HiRISE image shown on the first row of this figure on the left. And for a quantitative assessment of the super 3D result, we use multiple smoothed versions of a much higher resolution reference HiRISE DTM to compare with the target CaSSIS super 3D result and calculate the root mean squared errors and the structural similarity scores. And in this work, a sequence of boxcar low-pass filters with increasing kernel size are used to smooth the reference DTM, and subsequently the smoothed versions of the reference DTM are compared with the target DTM one by one, and from which we can expect that the RMC differences will first decrease as the features that in the target DTM fails to resolve are removed, and then increase as larger filters begin to remove features that are present in the target DTM. So similarly, the SSM scores will first increase and then decrease as their structural similarity increases and decreases during the continuous smoothing process. So eventually, the relative effective resolution can be defined quantitatively in terms of the smoothing kernel size that yields a minimal root mean squared error and the maximal structural similarity. And this minimal RMSE and the maximum SSM is hypersized to characterize the accuracy of the target DTM. The detailed assessment is described in paper, and as an example, the CaSSIS super 3D result that has been shown earlier has achieved an effective resolution of better than 2 meters per pixel from the 4 meters per pixel CaSSIS image. So finally, here again are the links to all the data products hosted in the ESA Planetary Science Archive and the papers of my talk today. And to draw some conclusions, I've So if you would like to access to the products, feel free to take some screenshot and use the QR code to go to the website. We have the Super-3D results for from CaSSIS and from a few HiRISE images covering the axial plane landing site area. So to draw some conclusions, I've introduced two separate deep learning based measures containing some traditional image processing techniques as well, and one for producing pixel scale high quality topography, and the other one for producing subpixel scale resolution enhancement of Mars orbital images. And a combination of the two measures can be used to produce subpixel scale topography from any of the existing NASA and ESA Mars orbital optical images. And such products can be used to assist scientific studies of Martian surface features and could also help engineering operations in the future. And the same techniques we have now applied to Moon as well, and if in the future can also be applied to other solar system objects, to exoplanet and astrophysical images as well. Right, thank you very much.